Okay, I'm going to talk about, I renamed the talk a little bit from computer memory systems to future computing platforms, because I think this would be a little bit more appropriate for a broader audience. But in the end, we're going to end up talking a lot about memory systems, since today's computing platforms are essentially limited by memory. I'm going to go through some self-introduction very quickly. This was already introduced, so I'm not going to talk about it. But this is our current research mission in my research group. We want to build fundamentally better architectures, and hopefully it'll be clear what we mean by fundamentally better architectures as we go into the future. I work in computer architecture, hardware, software, co-design, computer systems, bioinformatics, and security. These are 4 key directions we're following in my group: fundamentally secure, reliable, and safe architectures. We're going to talk a lot about that. Fundamentally energy efficient, more memory-centric or data-centric architectures. We're going to talk a lot about that also. And these 2 are in the slides, but I'm not going to talk about these fundamentally low latency and predictable architectures that are extremely important, of course, today, and architectures for artificial intelligence, machine learning, genomics, medicine, and health. Those are also quite important. I will mention some of these as we go through this talk. And I will also show this later on as well, but I wanted to point it out earlier. This is a transformation hierarchy, basically how we solve problems today. And if you look at where computer architecture is traditionally, it has been considered the interface between the hardware and the software and the underlying microarchitecture that implements that interface. But in this talk, I'm going to expand that, and I believe going forward we have to expand that so that we can solve the problems that we're facing. And we're going to look into a computer architecture spanning all the way from algorithms to underlying devices and circuits. So my axiom will be, if you would like to achieve the highest energy efficiency and performance, as well as reliability, security, etc., we must take this expanded view of computer architecture and co-design across the hierarchy from algorithms to devices and optimize across the hierarchy, as opposed to just focusing on single levels, and specialize as much as possible within the design goals to maximize efficiency and performance in given applications. Otherwise, I don't think we're going to achieve the goals of high efficiency and high performance of some really, really important scientific, medical, and technical problems that we have going into the future. I'm going to motivate those. So this slide is very busy. I'm not going to talk much about it. It's there just to show the research topics that we are working on in my group, because a lot of the things that I'm going to talk about are actually done by my research group, who works on broad research spanning applications, systems, logic, with architecture at the center of it. And we will touch upon some of these topics. And this is my research group. It spans ETH and Carnegie Mellon, although Carnegie Mellon is a much smaller part today because it's been 6 years since I left Carnegie Mellon. My last PhD student is going to graduate this year. She's actually Turkish. She got her BS from Bilkent, and she's finishing up a stellar PhD thesis. So after that, the group will be fully at ETH plus remote, of course, right, today. And if you're interested, you can read our newsletter, which is online. You can see the group over here in a newer version, let's say. So this is an important principle that I use to guide both my research and teaching. I believe teaching and research are very tightly coupled, in the sense that teaching drives research because you have to know the fundamentals really well if you would like to have a high and long-lasting impact in research. And research drives teaching because you have to input the research into the teaching so that you can keep students excited and also solve problems that are cutting edge. And I think this is an infinite loop. As you can see over here, you can keep repeating these 2 sentences over and over. And I try to practice this in my lectures. I start, for example, my freshman lectures in undergraduate, the class, by talking about the cutting edge research problems and motivating students that what they're going to learn as fundamentals are going to be the basic building blocks to actually solve those problems. And we focus a lot on insight, and I like encouraging new ideas. So if any ideas come to your mind during or after this talk, feel free to contact me or ask. I value new ideas and insights quite a bit. Even if the idea has already been done, it's important, I think, for people to come up with and create new ideas so that we can move forward. I think progress stops when we stop producing new ideas and insight. And as mentioned earlier, we have a lot of lectures online. This is a summary of some of the research topics. You can use these slides. I will put these slides later on my website, and you can point to some of these talks if you're interested in these topics. Okay, I have some other views on research and education. If you're interested, you can actually look at this interview that was done in ISCA 2019, a couple of years ago. And we discussed a lot of interesting topics over here. The students who interviewed me asked a lot of really good questions, actually, and I was quite happy with it in the end. Okay, so I'm not going to talk about this more. Let's jump into the topic of this lecture with this background. Essentially, I renamed this lecture as Future Computing Architectures, Challenge and Opportunities, so that we can give a more broad perspective of what's going on in computing architectures. And I think if we have to start fundamental, and I believe we have to start fundamental, we should really question, why do we do computing? And this is how I start my freshman lectures also. And my answer to this is to solve problems. And I believe this is a commonly accepted answer. If you reword this answer, it's really to gain insight so that we can solve these problems. And I would recommend people to look into Richard Hamming's famous book, let's say. He's actually the person who said, computing is all about insight, not numbers. In the end, you generate numbers to gain insight. Numbers by themselves mean nothing. Right? And if you extend this answer, why do we want all of this? We would really like to enable a better life and future, hopefully. Of course, technology is agnostic to ethics, right? In the end, technology has no morality. But I would like to think that we would like to use it for good. But of course, there will be cases where technology will be used for bad as well. But hopefully, let's focus on the positive in this talk and think about technology being used for good. So then the next question is, of course, how does a computer solve problems? And the answer in today's dominant technologies is really by orchestrating electrons. Today's dominant technologies are electricity-based, and electrons need to move so that things happen. Future computing technologies may differ, or past computing technologies may differ, but today's dominant technology is this way. Then the next question is, how do problems get solved by electrons? That's where we come up with the transformation hierarchy. We have a problem to solve. We have to model the climate, for example, so that we can understand what actions to take to minimize the impact humanity has on climate. And then we have to somehow communicate with the electrons to solve that problem. Of course, that problem is very vague, so you need to actually come up with a problem that can be actually solved. So you actually come up with an algorithm and then express it in a language and then run it on system software, and then that gets translated into the interface between the software and hardware. It gets implemented in a microarchitecture, logic, devices, and electrons. I'm not going to go through all of this. This is covered in freshman lectures clearly, but this is our transformation hierarchy. And the narrow view of computing architecture here is, for a long time, for decades, it's been the interface and the microarchitecture, its implementation. But as I mentioned earlier, we're going to take the expanded view. We're going to co-design algorithms, languages, system software, interfaces, microarchitecture, logic, and devices. So let me quickly define computer architecture, because there may be some folks who may not know exactly what it is. It is the science and art of designing computing platforms, hardware, interface, system software, and the programming model in a broader view. It's not only a science, in my opinion, it's an art, because we do not necessarily know the future, and future workloads differ. And we're designing computers that are going to be used 10, 20, 30, maybe 40 years into the future, right? That's why it becomes an art, because it's very difficult to model even the next year, right? And the goal is to achieve a set of design goals. For example, your design goal may be highest performance on Earth on workloads XYZ. You can define those workloads. It could be deep neural networks, for example, which is let's say, perhaps the most widely used workloads today. It could be the longest battery life at a form factor that fits in your pocket with cost less than some Swiss francs or Turkish liras. It could be the best average performance across all known workloads at the best performance cost ratio. So the last one is general purpose computation. The first one is very high performance computing. So supercomputers, for example, is in this category. And the middle one is more mobile computing, right? And clearly you can define many, many more design goals and create many, many computers. In the end, designing a supercomputer is very much different from designing a smartphone, but many fundamental principles are similar. In this talk, I will hopefully show and convince you that memory systems and storage system is the big bottleneck in the design of all computing systems that we have today. And we have to perhaps rethink the fundamental principles of computer design so that we can actually improve the design of computing going into the future. Okay, so these are some different platforms. They have different goals. I'm not going to go into details. This is an example platform that's very popular, clearly. This is another platform that's a joke, of course. It's from Mr. Bean, but it's a self-driving car from Mr. Bean, as you can see. It would be nice if we actually could trust our cars as much as Mr. Bean trusts this car. I don't believe that I would trust any self-driving car today to be comfortable enough to actually sit on top of it like this. And this is another self-driving car, actually. This is one of Google's earlier cars. You can see how the computing power that's put into the back of this car so that it could actually self-drive. This is a data center, which is different from a supercomputer. This is one supercomputer in China. Let me actually tap my thing. It's not, somehow my light has gone. But anyway, and this is Google's tensor processing unit. This is actually, I'm sorry, I need to go and turn on my light over here because I cannot see very well. Just a second. Okay, this is much better. It was supposed to be a smart light, and it's clearly it's not performed really well at this point. Okay, but basically this is Google's tensor processing unit, which is one of the earliest machine learning accelerators that are used in all of Google's data centers. This is Tesla's essentially machine learning accelerator that's used in self-driving computers. You can see that different platforms are actually using specialized computation systems today. And you can see that a car company like Tesla is designing its own chips. This is really the trend going into the future. Many companies will customize, or people potentially will customize across the stack and use their own chips for the problem that they're trying to solve. And you can see that there are multiple chips for better safety over here. So, okay, my axiom, as I mentioned earlier, is going to be that to achieve the highest energy efficiency and performance, we must take the expanded view of computer architecture. So we must really co-design across the hierarchy so that we can optimize as much as possible to minimize the energy waste, maximize the performance. So, and we can specialize within the design goals. Then the next question is, of course, what kind of a future do we want? What kind of principles should we look at in the design of future computing platforms? And this brings us to really issues we're having in systems as well as problems. And I think one important issue is reliability, security, and safety. I'm going to talk a lot about that at the beginning of this talk. So if you look at this bridge was built in 1940. It's the Tacoma Narrows Bridge. It's on Tacoma Narrows over here. It's in Washington. I used to be at Microsoft Research, and this is a bridge that I did not cross because this bridge got destroyed like this because of let's say, a bit flip or equivalent of a bit flip, a reliability problem that was in this bridge. And what happened was there was a elastic flutter. And as a result, the bridge was doing this, going up and down, and eventually it snapped at some point, and it looked like this. So this is clearly a reliability problem that leads to safety issues and security issues. And this is a lucky one because there was no human life fatality over here. But there are many bridge incidents in the world that led to fatalities, clearly. I like thinking about reliability, security, and safety together, even though they're different concepts. In this particular example, they become very similar. I like talking about this because it's good to think about this as infrastructure. Clearly, bridges are infrastructure. Computing is a much bigger infrastructure. Bridges are only in a small fraction of in our lives, right? We cross them once in a while, yes, but if you do the calculations, the probability of you falling down in a breaking bridge is not very high. But the probability of you something bad happening to you because a machine learning engine or some other computing system doing something wrong because of a reliability problem or a security problem is much higher than that. And it's going to be increasingly higher. So we need to be actually very cognizant of how we build this computing infrastructure going into the future so that reliability problems like this don't happen much, and they don't lead to security problems, they don't lead to safety problems. And self-driving cars is clearly one example, but we're going to increasingly trust, for good or bad, these computing systems with our lives going into the future. And I don't think that's a good idea if you don't design them in a fundamentally better way. And this is another example that I use. These folks are actually constructing New York at the end of the First World War, and they're sitting on this rod over here. They're happy right now, but what happens if there's a bit flip on this rod? They will not be happy in the next second, right? So I think of security as preventing unforeseen consequences, and this is a very general definition of security, but I think we should really strive to look for achieving this sort of security, because our lives are going to depend increasingly more on the computing infrastructure that we're designing today. So basically, a big challenge and opportunity for the future is how to design reliable, secure, and safe systems. And I'm going to talk about this as we go forward. I think an important, maybe equally important or more important challenge is this, which is, do we want a world that looks like this? Sustainable, efficient, beautiful, that we want everyone to live in? Or do we want a world that looks like this? This may be on top of this wars, right? I would argue that we would like a sustainable and energy efficient world. And that's going to be very important into the future as well, because our lives, again, depend on it. On top of this, I think we have many difficult problems to solve. Clearly related to the previous one, we want to understand the climate and what's happening to it, what kind of problems we're causing. And that's not an easy problem, especially if you want to model long term. We want to understand problems we have created, like congestion. We want to understand natural problems, and so that we can actually take advantage of the best of what we understand. Intelligence, biology, bioinformatics are examples of this. We want to solve issues like public health or personal health. Clearly, this is very important this year and next year and previous year. And we want to understand also genome analysis. And I think these are clearly, aside from being secrets to life and intelligence, these can have a significant influence on people's well-being, medical and scientific advancements. And there are many, many other problems, clearly. I'm not going to talk about them, but if you're interested in genome analysis, we work a lot in this area. And this is a recent survey paper that we wrote that talks about how to accelerate genome analysis. I'd be happy to talk about that separately. And if you're really interested, you can actually watch one of my lectures that I recently delivered at the Technion that talks about genome sequence analysis in more detail. This is the state of the art, perhaps, on accelerating genome analysis. And there are more lectures that I will point out over here that I'm not going to talk about. But basically, there are many, many problems that we want to solve as a humanity. And all of them require high performance, because these are some tough and difficult problems. And we want to solve all problems. We don't want to be selective about them. Okay, on top of that, I think a very specialized problem is really health and medicine. And how do we enable personalized, specialized health to the masses so that we can have a much better future? I'm not going to go into a lot of detail over here, but this needs to be private as well. And there's a lot of issues here, like how do you understand the genome? How do you understand proteins? And that how do you actually take advantage of new genome sequence analysis technologies like this so that we can actually, for example, the doctor can deliver a critical drug that is personalized to the person, that they know that it doesn't have side effects, or that they know is going to work, because you may have very limited time to actually act at that point in time. So this all requires very, very high performance and very high energy efficiency, and we're striving towards that. And it also needs to be personalized and private, I think, because we have a lot of privacy issues. Unfortunately, as I said, technology can be used for bad. Maybe by designing personalized and private technologies, we can actually disable it from being used for bad. And this has to be done in every aspect of life, in my opinion: health, medicine, spaces, devices, robotics, wherever you can imagine. It's going to be a much more tightly integrated technology to people, as opposed to decoupled from the people. So what is this lecture about? This was all a preamble. This lecture is really about questioning what limits us in the design of best computing architectures for the future, hopefully providing directions for fundamentally better designs, and advocating principled approaches. And I'm going to try to do that in the remaining time, focusing on especially memory systems. One thing to keep in mind is that we will have increasingly demanding applications, and applications will always come because people are creative. They're going to always dream about applications, and they will come. I don't think they will, as applications continue coming, they push the boundaries. Computing platforms will become increasingly strained. A perfect example of this is the machine learning revolution that happened around 2012 or so. Machine learning, clearly there were a lot of algorithms that were designed for machine learning, but those algorithms, training algorithms, were not possible to efficiently execute in old hardware that was not good enough. But as the GPUs, graphics processing units, took over time, machine learning folks figured out that they could train these algorithms on GPUs, and they could do inference on these GPUs in a much faster and much more efficient way. As a result, machine learning revolution is right now going on today. The machine learning revolution, at the core of it, is really a computer architecture or hardware-driven revolution. If the high performance, systems like GPUs did not exist, I do not believe that revolution would have happened. You needed to have a high performance enough system to enable machine learning. Okay, so the key realization, given all of this, is that modern systems that we design today are bottlenecked by data storage and movement. And I'm going to talk about why they are in the rest of the talk and how we can solve the problems. So my focus in the rest of this talk is going to be data storage systems. And I'm going to especially focus on the memory size of it. If you look at a traditional computing system, it has processors, main memory, and storage. Main memory and storage are kind of merging today, but we're going to focus a lot on main memory. And main memory exists in all systems. Essentially, it's a critical component of all computing systems: server, mobile, embedded, desktop, sensor. If you want the system to become high performance and more efficient, the main memory system must scale in many, many dimensions in terms of its size, technology, efficiency, cost, and management algorithms, so that we can maintain the performance growth and technology scaling benefits that we've been used to for a long time. It doesn't matter what kind of computing unit you attach to it. It could be general purpose processors, it could be specialized, it could be FPGAs, it could be GPUs, it could be specialized machine learning accelerators. In the end, all of them are bottlenecked by main memory. That's why main memory is so important. In fact, if you look at the cost of a system today, more than half of the cost of a system is really spent on main memory. If you look at big data centers, for example, and that's increasing going into the future. Okay, so basically the problem today, computing is bottlenecked by data. And data is really key for key applications. Whatever you can imagine, important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And data is increasing on top of this. We can generate more data than we can process. I'm going to give you some examples of these workloads. These are some more traditional workloads. And they have all been shown that memory is a huge bottleneck in them. These are some mobile workloads that many of us use, knowingly or unknowingly. And they've all also been shown that memory is a big bottleneck in them. And these are the genome analysis workloads that lead to scientific discoveries and medical advancements. Again, memory is a big bottleneck in them. And these are some emerging technologies going into the future. Memory becomes a more bottleneck in them. Let me give you one example study that we've done together with Google. This took us about 1.5 years or so. We worked together with Google on this. And we analyzed some mobile workloads that are used in Google consumer devices, but any kind of consumer device has equivalents of these workloads. And we found out that more than 60% of the entire system energy spent on these workloads executing on mobile devices is spent on data movement. And we're going to try to solve this problem by minimizing the movement of data. Okay, memory is critical for performance, energy. It's also critical for reliability. This is a study that we did with Facebook about 6 years ago, actually more than 6 years ago. The paper was published 6 years ago, as you can see. Basically, we studied the memory errors that happen in all of data centers that Facebook has, and that's a lot of data centers. It's a lot of memory, actually. It's Facebook doesn't allow us to actually say exactly how many because they're concerned that it affects their stock price, etc. Maybe they should be concerned more about privacy issues or something like that. But essentially, across all of these memory devices that we examined, we find a very strong correlation between the memory chip density, DRAM chip density employed in the server, and the failure rate that you see in the server. So this is a very strong correlation, as you can see. As chips get denser, as memory capacity increases, system reliability reduces. This is because you get more errors in memory. And this is fundamentally problematic because cells become closer to each other and you get more vulnerable to noise. That's why you get more errors. So systems become less reliable. Clearly, this is going to be a big problem when you actually have a self-driving car, for example, and you want to add more memory so that you can run better machine learning algorithms on top of it. This is going to be another problem if you have these personalized genomics workloads that crunch on a lot of data. If you actually get errors in the system that either destroy what's running or that go undetected, then you actually have significant problems. Okay, let me reword the realization that I mentioned earlier. Today's modern systems today are bottlenecked by memory, essentially. And let's focus on memory in the 4 key issues that I discussed earlier. So I'm going to talk about fundamentally secure, reliable, and safe architectures and how memory plays into it. I'm going to talk about fundamentally energy efficient architectures and how memory plays into it. Unfortunately, we will not have time to talk about low latency and predictable architectures, as well as architectures for AI, ML, genomics, medicine, and health, because we don't have enough time. But let's jump into the first 2. We may not have enough time for both of them. So I'm going to motivate these parts by actually referring to human psychology as well. So this is a very famous American psychologist, Abraham Maslow, who dedicated his life to understanding why people do the things they do, essentially human motivation. And he is more famous for this hierarchy of needs than his face, clearly. And he basically theorized that humans operate with a hierarchy of needs. And fundamentally, at the bottom of the hierarchy, you have to have your physiological and safety needs satisfied before you can think about highest forms of abstract art, for example. And that's essentially similar to computers also, in my opinion. We need to start with reliability and security, because if you do not have a reliable, secure, and safe system, maybe nothing else matters because everything is broken. And that brings me back to the picture that I showed you earlier, the Tacoma Narrows Bridge that broke in 1940, 6 months after it was built. And you can consider this a bit flip that's occurring in memory that leads to a safety, security, and reliability problem that we cannot recover from. And I believe we need to fix the mentality by thinking about security, safety, and reliability in a more stronger way in the systems that we are going to depend on. So basically, the problem is that we do not seem to have design principles for guaranteeing reliability, safety, and security. I omitted safety over here, but I should have put it over there also. But we really should going into the future. So let me give you examples from memory. I already showed you this example. As memory scales, it becomes unreliable because cells become closer to each other and you become more vulnerable to noise. And this is because we have problems with the memory technology that's used to build our main memories with. And this is the dynamic random access memory technology, which was invented in 1965 by Bob Dennard at IBM. And it's still the most important technology that's used by almost all main memories today. And if you look at this technology, I'm going to turn on my light again. Sorry about this. Okay. Okay, so hopefully I've fundamentally solved this problem. Okay, basically the DRAM technology consists of DRAM cells. And if you look at DRAM cells, it stores charge in capacitor, and there's an access transistor. So, and then you have billions of these cells in your cell phone, for example, or computer that are connected in some way. So this is a simple data storage device. For this to work, both the capacitor should work and the access transistor should work. Both of them should be reliable. The capacitor must be large enough for reliable sensing. The access transistor must be large enough for long data retention time. Unfortunately, as you reduce the size of the cell so that you can cram more capacity into your memory chips, both of these properties become difficult to maintain. As a result, as DRAM cell becomes smaller, it becomes more vulnerable to noise, it becomes less reliable, and then you can start getting errors. So we built a lot of real hardware infrastructure to understand such issues. Essentially, these are our FPGA-based infrastructures, which we can program to test many, many memories at the same time. This is another example of this infrastructure. You can see that it's scalable. And we actually open sourced this infrastructure more recently in 2017 so that other people can actually make use of it and test memories. And other people, both in industry and academia, are actually using this today. If people are interested in using this infrastructure and actually understanding different properties of memory, we'd be happy to help. So while we were actually doing a lot of testing on this infrastructure, we stumbled upon a curious phenomenon, which is called the DRAM Roadhammer phenomenon in 2012. And we published the paper in 2014. And essentially, the phenomenon is something that should not happen. It's basically the fact that you can predictably induce errors in most DRAM memory chips in a very, very controllable way. As I said, this is called the DRAM Roadhammer phenomenon. This is a simple hardware failure mechanism that can create a widespread system security vulnerability and also safety vulnerability clearly. And people are writing popular papers, articles that look like this now. This was published in 2016 based on our work. And this person at Wired magazine says, forget software. Now hackers are exploiting physics. And this is a very good high-level characterization of Roadhammer. So let's talk about what Roadhammer is. It's essentially disturbance errors. Basically, whenever you need to access memory consists of rows, and you need to first activate one row, which means that you need to apply high voltage to the row of cells that are connected to the row. And this is called opening or activating the row. Now, there are some adjacent cells also. And then you may apply low voltage to this row so that you can access some other row. Now, if you keep doing this repeatedly, activate precharge, activate precharge, activate precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, many times, by just reading this row, it turns out in most modern DRAM chips, adjacent rows have some bit flips, vulnerable bits that get corrupt. Basically, these bits change from 1 to 0 or 0 to 1. This clearly should not happen because you're not accessing these bits. You're not writing anywhere in memory. By just accessing this row many, many times, you're causing some disturbance and some cells, you're basically causing data corruption, which should not happen. You're changing some data that you're not supposed to change. And we showed that more than 80% of the chips that were manufactured by 3 major DRAM manufacturers actually have this problem. And this is a scaling problem because it did not happen before chips that were manufactured in 2010. Older chips did not have this problem. Newer chips have the problem. And all of the chips that are manufactured between 2012 and 2013 are actually vulnerable to this problem. So the problem is cells are becoming closer to each other. As a result, the number of times you hammer a row to actually induce these bit flips is reducing. As a result, it's much easier to induce these errors in the system. So why is this happening? I'm not going to go into a lot of detail, but basically DRAM cells are too close to each other. They're not electrically isolated from each other. Access to one cell affects the value in nearby cells due to the electrical interference between the cells and the wires used for accessing the cells. This is also called cell-to-cell coupling or interference. For example, when we activate or apply high voltage to a row, an adjacent row gets slightly activated as well, and vulnerable cells in that slightly activated row lose a little bit of charge. And if Roadhammer happens enough times, charge in such cells gets drained. And this should not happen again. Higher level implications. This has enormous implications in upper levels of the transformation hierarchy because user gets affected, right? In your memory now, some data structure gets corrupt and user doesn't even know about it. And this corruption can be used to take over a system to make it less secure. So let me give you an example of why this is a big problem at the high level. So this is a real program run on Intel and AMD systems, x86 systems. You can actually download this program from our GitHub. Actually, I would suggest downloading Google's version of the program because they improved our program and made it much better. But basically, what this program does is it chooses addresses X and Y such that they map to the same bank in memory. It basically hammers them. Does this repeatedly. And then if the chip is vulnerable, you get errors all over the chip. And then you can do something, take over the system if you know what you're doing as an attacker. So we showed in 2013 and 2012 that in real systems, you can get these errors, Intel, AMD. There's nothing special about Intel and AMD. Any system that has vulnerable memory actually has these errors. Later, other people showed that. So this is a real reliability and security issue in real memories today. And when we wrote the paper the first time, we said that memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. And we said that someone can hijack your computer by taking advantage of these bit flips that we showed. And while we were working on it, these good folks from Google Project Zero, they actually showed exactly that. They basically took our work. This is a copy paste from their blog post. They also have a nice black hat presentation about it. I would recommend everybody to watch it if they're interested in beautiful system security engineering. They basically said they learned about the problem from our work. They replicated our work and they showed that Roadhammer exists. And they basically built two kinds of attacks. One attack is really, really interesting. They basically are able to use a user level program to induce bit flips in x86-64 Linux to gain kernel privileges. Essentially, they become root on Linux. And the way they do it is beautiful system security engineering. I'm not going to go into detail, but this process is able to induce bit flips in its own page table entries. So it's able to gain write access to locations that it's not supposed to gain write access to. So it's basically able to, now after that point, you can write to entire memory. You can read from entire memory. Basically, you can get access to all kinds of information on that computer. Plus, you can become root so that you can actually kick out the user itself. So this became famous as a DRAM Roadhammer vulnerability. And I like this analogy from a hacker. This is a very famous hacker on the internet. They basically say that Roadhammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So you're not actually opening the door you were after, but you're banging on the door, some other door, or some wall such that the vibrations magically open the door. And this is a beautiful analogy, I think. So later, a lot of people built attacks. These are nice works. I'm not going to go into the details of this because we don't have time. This work from TU Graz, this work from Vrije University in Amsterdam. They basically showed that they can gain control of a smartphone easily using Roadhammer. They can do it much faster using GPUs. They can do it remotely with a remote computer. And other people show that even if mitigations are put in, you can actually leak significant private information. And recently, other folks showed that they could use Roadhammer to essentially deplete the intelligence of deep neural networks by reducing their accuracy significantly. So basically, the bridge analogy that I gave you earlier, bit flips, turning our intelligent infrastructure into something completely unreliable is happening. And this is another example of depleting the intelligence of a deep neural network using Roadhammer, as you can see. These folks in 2020 showed that without Roadhammer, the accuracy of the network is more than 90%. With Roadhammer, the accuracy drops to 10%, which is not good. Okay, so maybe there are other security implications. Maybe this is a solution. I would not recommend this as a solution, clearly. I think there are better solutions. This is not a good solution that I would recommend, but this is the solution that is implemented in real systems today, which is really refreshing the system more. But this is not a good solution. But still, this is the only solution direction that we have without disturbing the system. And I like Apple's security release over here because they give credit to our original paper, as you can see over here. Okay. So I believe a good solution direction for this kind of issues is designing principled designs. We want to design fundamentally secure computing architectures that can predict and prevent such safety issues. Let me give you our idea of the solution, which is very simple, very limited intelligence, but still more intelligent than just refreshing everything much more frequently. This is called probabilistic adjacent row activation. So after closing a row, the memory controller activates the neighbors of the row with a low probability. And if you do this, you get a very strong reliability guarantee. And if you're paranoid, you can actually increase the probability, of course, at the expense of performance and energy. And we show that this is very low power, low performance overhead, low cost, and low complexity. And there are different implementation options. I'm not going to talk about this in detail, but essentially it's done today. Both of these are done today, although they're not done in the way we suggested. As a result, there are some security issues. But I will show that Intel actually implemented a variant of our solution in a way that is more primitive than we envisioned. Basically, this hardware Roadhammer protection that you can select in the BIOS of a computer is essentially probabilistic adjacent row activation, and you can select your activation probability in the BIOS. We thought you would do this automatically in the system such that the user is not exposed to this. So if you're interested in Roadhammer, there are more lectures. I'm not going to go into the details of these old works over here, and clearly there are a lot of papers. And we actually wrote recently a more retrospective that talks about all the research that we know of that covers Roadhammer. Now, in 2020, a lot of interesting things happened. So at some point, DRAM manufacturers said they solved the problem, but it turns out they did not really solve the problem. So right now, Roadhammer is a big issue again this year. So we're working on new solutions together with industry and academia. So in this work, we showed that Roadhammer is getting much worse. We examined more than 1,500 memory chips. And we basically said that vulnerability is increasing based on experimental data. Some of the weakest cells fail after only 4,800 activates. So basically, when we tested in 2012, this number was 139,000. Right now, you can actually induce a bit flip after 4,800 hammerings, which is not good because the vulnerability is easier to exploit. And then this is also becoming worse, and the mitigation mechanisms are unfortunately not effective. In another work that was published in the IEEE Security and Privacy Symposium, we showed that so DRAM manufacturers, as I said, implemented some solutions that are obscure. They did not talk about how they solved the problem, but they basically said, our chips are Roadhammer free. In this work, we show that the chips are actually not Roadhammer free. Basically, if you're an intelligent attacker, you can reverse engineer what's happening inside the DRAM chips, and you can actually take over the DRAM chips, even though they're advertised to be Roadhammer free. And I'm not going to talk about this in detail. This is a fascinating topic. As a result of these two papers, now industry is much more serious about designing secure and safe architectures today, because now they're having finally a serious conversation about how can we actually have a fundamentally secure and safe DRAM system. And there's another paper that I'm not going to talk about, which we did with Microsoft, that tries to ask the question, can we somehow declare a DRAM chip Roadhammer free? And the answer is basically no. There's no good testing methodology today to enable this sort of qualification of a DRAM chip. So we also work on a lot of solutions, and this is a work that's coming up in HPCA 2021 as a solution direction, which I believe is very promising. I'm not going to talk about this in detail, but I will refer you to more detailed lectures on Roadhammer. And I recently actually delivered a keynote talk at the High Peak conference that talks about the story of Roadhammer in more detail. If you're interested, there's a lot more detail in this talk. So let me talk about the future of main memory reliability before we focus on the next topic. Today, DRAM is becoming less reliable and more vulnerable. There may be other problems that are appearing. They may be going unnoticed. Some errors may already be slipping into the field. Clearly, Roadhammer has slipped into the field. Retention errors, read errors, write errors, and other errors may be slipping into the field as well. So these errors can also pose security vulnerabilities, in my opinion, and we need to take them very seriously. And all memory technologies are vulnerable. It's not just DRAM, it's also flash memory, and emerging technologies that are supposed to be replacement or augments to DRAM are also vulnerable. I'm not going to talk about this in detail. So the question is, of course, how do we keep memory secure going forward, since we're going to critically rely on it in our intelligent infrastructure. I believe this is a three-step methodology. I'm not going to go through the details of it. We need to understand, meaning we need to develop methodologies for failure modeling and discovery. This requires modeling and prediction based on real device data. We need to architect. We need to have a good architectures that can actually ensure that we can enable security. This requires good partitioning of duties across the stack. And we need to design and test rigorously. We have to have principled design, automation, and testing methods. Some of it is online. This needs to have high coverage and good interaction with system reliability methods. So we're doing some of this, as I mentioned earlier. We're doing some of this in flash memory. Also, if you're interested in flash memory, I'd be happy to talk about it separately, but you can also refer to this work that we have written, invited to the proceedings of the IEEE a few years ago. There are also two other solution directions that I'm not going to talk about, but new technologies are clearly very interesting. Unfortunately, they all have their problems. But another interesting direction is embracing unreliability. Basically, if memory is going to be not reliable, or if it's going to be very costly to make some part of memory reliable, why not have most of your memory to be unreliable and actually adapt to it? Design your application such that you store data intelligently across the reliable versus unreliable parts of memory. And we showed that this actually could be a very good direction going forward. But all of these directions actually require co-design across the hierarchy, like I discussed earlier. You need to think about algorithms all the way to devices. So this is the first challenge and opportunity for the future that I wanted to discuss, which is fundamentally secure, reliable, and safe computing architectures. Now, an important takeaway from this is we want intelligent controllers to handle security, safety, and reliability. I think going forward, we want intelligent controllers to actually do much more than that, to enable energy efficiency and more memory-centric architecture. So I'm going to focus the remaining part of the talk on fundamentally energy-efficient or memory-centric architectures. And again, I'm going to bring in Maslow's hierarchy of needs, and I'm going to deconstruct what I said earlier. Reliability, security, safety, they're extremely important, no problem, yes. But if you don't have energy to survive, who cares about reliability, safety, and security? So maybe energy is more important, arguably, depending on the situation, right? So basically, we're back to the picture that I showed you earlier. Do we want a world that's sustainable and efficient, or do we want a world that we cannot live in? I would argue that we want the best of both worlds. We want sustainable and energy efficient, but we also want high performance. Unfortunately, today, data access to the memory is a major performance energy bottleneck that is causing sustainability and energy problems. Today's computing systems are designed with principles that cause great energy waste because we move data a lot, because the processor needs to process the data. To be able to do the processing, the data moves from the disk to the memory and then to the processor. As a result, data movement actually consumes a lot of energy because the disk and the memory system don't have capability to do processing. And this causes great energy waste. And this causes great performance loss as well because data moves a lot, and that is high latency. Now, we create a lot of complexity in our systems to overcome that performance loss. I'm not going to go into the details of this, but we create very sophisticated, complex caching hierarchies, complex software, complex multi-threading mechanisms, complicated out-of-order execution engines, complicated prefetching mechanisms. All of that add to complexity so that we can tolerate the performance loss. But these also add power. As a result, they waste energy. And especially when they don't work, they don't improve performance and they waste energy. So actually make us go into a vicious cycle. We have this performance problem. We try to add more complexity to solve that performance problem. We already waste a lot of energy. We doubly waste energy so that by adding complexity. So we're in this vicious cycle that we need to break. And whenever you have a vicious cycle, the way to break that vicious cycle is really to fundamentally understand the problem. And really the problem is processing of data is performed far away from the data today. If you look at a computing system, fundamentally it consists of three components: computing units, communication units, and memory and storage units. Today, we have heavily optimized the computing unit. Everything gets processed in the computing unit. We're very much processor-centric, and it's considered the master. All of the data storage and communication units are essentially dumb. They are not able to process the data, even though they have access to very large amounts of data. So as a result, the data moves a lot. And as a result of this, memory becomes a huge bottleneck. And we know that, actually. This is Dick Seitz, who was the chief architect of alpha processors. He wrote this one-page article in Microprocessor Report after his team designed the fastest processor of its time in 1996. He basically says that it's all about memory. And he basically said in this article that we designed this very sophisticated processor. It is capable of finishing 4 instructions per cycle, but unfortunately, it's finishing 1 instruction every 5 cycles, approximately 5 cycles, in this important workload. Basically, it's operating at 1/20th or 5% of its capability. Why? Because it's waiting for data to come back from memory. And he finishes the article saying, I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And fast forward about 10 years, this is data from my own PhD thesis. I developed something called run-ahead execution with my co-authors. Basically, we showed the same thing. We looked at the workloads that Intel used to design its systems with at the same time. And we showed that most of the time, the processor is waiting for memory. Now, if you don't believe me, if you don't believe DeepSight, since most people today somehow believe Google, I don't know why, Google showed in this beautiful paper exactly the same thing. Basically, they analyzed their own workloads that are run on data centers. You can see these are some really interesting workloads, video, search, indexing, Gmail, etc. They basically said most of the time, the processor is waiting for data. And only 10 to 20% of the time, the processor is actually finishing instructions. And there's great analysis in this paper. I'm not going to go into details of it. Clearly, we're actually experiencing the perils of processor-centric design. We have grossly imbalanced systems because processing is done in only one place. Everything else stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And on top of this, we make our processors and accelerators more complicated and bloated. And this leads to more energy inefficiency, low performance, and complexity. And as a result, we have this picture that looks like this. Essentially, this is my cartoonish picture. Most of the system is really dedicated for storing and moving data. We call this a computing system or a processor. But if you look at the real estate hardware that we dedicate in a computing system today, most of it is really for memory, interconnect, and storage, not processing, basically. Actually, less than 5% is dedicated for processing. So this should be an indication that we're doing something wrong in the design of our systems. Okay, so let me give you 3 key system strands. Today, as I mentioned earlier, data access is a major bottleneck. Applications are increasingly data hungry. Energy consumption is a key limiter, and data movement energy dominates compute. Let me demonstrate data movement versus computation energy. This is a slide that I borrowed from Bill Daly. Basically, we're going to look at the cost, energy cost of different operations. I'm going to focus on a 64-bit double precision floating point operation. These are old numbers, but the conclusions remain. Maybe numbers have changed. Actually, they have changed. But a 64-bit double precision floating point operation consumes 20 picojoules today, but a DRAM read or write is 800x higher energy. So a memory access consumes 2 to 3 orders of magnitude the energy of complex addition. So then the question is, does it really make sense to move the data from the memory to the processor so that we can process it? And there's actually a lot of historical thinking that we can do over here. If you go back 70 years ago or 80 years ago, the picture was not like this. The picture was that a DRAM access actually was much cheaper 80 years ago compared to computation. It was about 2 orders of magnitude cheaper. So why did we come this way? Because of technology scaling. So Moore's law and technology scaling, Dennard scaling, has enabled us to reduce the cost of logic significantly in terms of latency and energy, but it did not allow us to reduce the cost of memory device access, latency, and energy, and interconnect. As a result, logic became much faster over the course of 70, 80 years, but memory did not, and its energy did not improve as much. And as a result, we have this picture today. So maybe we should be rethinking how we design systems now that the trade-offs have changed dramatically. And this is not just Bill Daly talking about it. There are other works that have been written that talk about how much costly it is to actually do a memory access compared to a simple add or a complex add, actually. And as a result, as I mentioned earlier, we see pictures that look like this. More than 60% of the entire system energy is spent on data movement. So basically, I will argue that we do not want to move data in our systems. We would like to minimize the movement of data. And to be able to do that, we need a paradigm shift to enable computation with minimal data movement. We would like to compute where it makes sense, where data resides, not just in the processor, not just in the accelerators, but across the system where data resides. And we want to make computing architectures more data-centric. So I'm going to talk about the goal of processing inside the memory. So memory is a special place. Of course, we would like to do this in the disk. We would like to do this in the interconnect. We would like to do this in the router. We would like to do this in the caches. But I think memory is very special because memory is large today. It's low latency reasonably compared to the disk, for example. And a lot of applications today are designed to be fit inside the memory. They're in-memory databases, in-memory graph processing, and media processing engines, for example. And the idea is memory now becomes an active component that can operate on the data. You don't need to move the data to the processor. So processor can actually ask the memory, can you execute this for me? And the memory says yes, so it executes and returns the results. Clearly, this is a paradigm change. There are many questions. How do you design the memory and the controllers? How do you design the processor and in-memory units? How do you design the interfaces between the software and hardware to enable this? How do you design the system software, compilers, and languages to enable this? And how do you design actually the algorithms and rethink the theoretical foundations of computing to enable something like this? I'm going to get back to the theoretical foundation in a little bit. But before that, this is really a cross the stack problem, as you can see. We would like to rethink the algorithms all the way to devices, but we want to do step by step. Let me talk about the theoretical foundation a little bit. Probably most of the audience here has taken some theory of computation course in their computer science or computing engineering background. If you look at how we think about the complexity of algorithms, it's very processor-centric. What do? The big O notation, for example, is counting operations. But if memory is the big bottleneck, counting operations may not be important, right? Maybe we should be more data-centric in the theory of computation. This is how ingrained the processor-centric paradigm is into our thinking. So we really need to change our thinking so that we can design much more sustainable and efficient systems going into the future. Okay, let me give you some examples of in-memory processing very quickly, just to show you that what's possible. So I would like to start simple. I would like to not even do computation first. I'm going to talk about data copy and initialization because this is really important, actually. Whenever we, for example, fork a process, we copy a lot of data. Whenever we initialize a page, we copy a lot of data. Whenever you do checkpointing, virtual machine cloning, page migration, and there are many, many other applications of it. And Google, in the earlier paper that I mentioned, showed that approximately 5% of the entire execution cycles across all of their workloads in all of their data centers is consumed by just these two function calls that do copying. So this is actually a huge number if you consider two function calls, right? There are thousands of function calls that are done by applications. Only two of them consume 5% of the cycles. This is not good, basically. So how do we do data copy today? If you want to copy a source page, the white page, to the gray page over here, today we go through the processor. This is probably not a good idea. Basically, we bring the source page and the destination page and then write back the destination page, right? So this is high latency, clearly, because you move data a lot. This is high bandwidth utilization on perhaps the most important bandwidth constrained component, memory bus. And then this caused cache pollution, but I could eliminate that by doing this through the direct memory access engine today. And this caused a lot of unwanted data mode, because imagine you have a system, you're initializing a 1 terabyte database. 1 terabyte is a big number. Do you really want to go through the processor to do this initialization? Because you're not going to use any of those pages that you're touching. So even a small data copy today, 4 kilobyte page copy done through the direct memory access engine, not going through the caches over here, consumes about 1,000 nanoseconds and 3.6 microjoules today. So if you show this picture to a child, let's say 10 years old, and ask the question, am I doing something wrong here? I bet if they are, most children are very intelligent, actually, they will probably answer you saying, well, why don't you just do it in memory? And I think at this point, we should really be thinking like a child and doing things in memory, doing the copy inside the memory without disturbing any other component in the system. And the idea is that we can exploit the internal connectivity in memory to make this fast. It can be very low latency because we're not going through the system. We're actually exploiting something inside the memory. We're not using the data bus over here, so we're leaving the system so that system can use it for more important things. We're not causing cache pollution or pollution in any of the structures over here. And we're not causing any unwanted data movement. We're moving the data only when it's really needed. And I'm going to show you a mechanism that reduces the 1,000 nanoseconds to 90 nanoseconds. That's more than 11x improvement. And 3.6 microjoules to 0.04 microjoules. That's more than 70x improvement with simple, very, very simple changes to memory. I'm not going to go through the details of it because that becomes very technical, but I'll give you the basic idea at a high level. Essentially, if you look at memory, it consists of rows that I showed you earlier. Now, the idea is if you want to copy one source row to a destination row in the same DRAM subarray, you first activate the source row, which brings the data into sense amplifiers called row buffer. And then the second idea is to activate the destination row. Basically, if you do this, you implicitly deactivate the source row, data stays in the row buffer, and once you activate the destination row, the sense amplifiers in the row buffer drive the destination row. So by using the row buffer as a temporary place to move the data, but not moving the data outside the chip significantly, by doing 2 consecutive activates, we can do this very, very efficiently. And this is negligible hardware cost, and recent work actually showed that you don't need to change the DRAM chips to enable this in more or less reliable fashion. You can actually do this in commodity DRAM chips, even though DRAM chips are not designed to do this. You can do this by violating some DRAM parameters. So it's actually very, very interesting that you can do it in real chips. And the benefits are very high. Basically, you get more than 10x reduction in latency, and you get more than 70x reduction in memory energy. Ignore these parts. These parts makes it more general. If the source and destination pages are in different locations, like in different banks and different subarrays, it becomes less efficient, but we actually develop methods to make it much, much more efficient closer to this red bar over here today. I'm not going to talk about those, but I'm going to refer you to the early row clone paper that talks about this. And you can find a lecture about row clone that talks about the recent work that has built on row clone on my website as well. Okay, so the thinking over here is something different. Basically, today we're thinking of memory as an accelerator. We're used to building many accelerators on the core side. You can have CPUs, GPUs, machine learning accelerators, video accelerators, audio accelerators, and who knows what else, self-driving accelerators. But why not build some accelerators on the memory side such that they can do what they're really good at? And the memory is really good at data copy initialization, as I showed you earlier. And memory can be thought of as a similar as a conventional accelerator. But of course, this accelerator has a lot more capability that none of these accelerators can have. All of these accelerators over here on the left side is bottlenecked by the memory bus. These accelerators over here are not bottlenecked by the memory bus. As a result, they have low latency, high bandwidth, low energy access to large amounts of data storage. And that's the big opportunity. So let me go a little bit further. I'm not going to go into a lot of detail over here, but actually we can support in DRAM and or not as well. So we can actually have functionally complete computation in DRAM in a bulk bitwise manner. We can do this at low cost. And we can use the analog computation capability of DRAM memory for this. And the key basic idea is you can activate multiple rows concurrently, and that leads to computation. And this is based on the electrical operation principles of DRAM based on chart sharing. I'm not going to go into more detail because we don't have time, but this leads to 30 to 60x performance energy improvement in these bitwise operations. And if you know some basics of Boolean logic, clearly you know that these are functionally complete. So if you can express your algorithm in terms of these operations in a nice manner and lay out your data nicely, you can actually map any algorithm on top of this. And you can read our paper that talks about this. And new memory technologies like phase change memory, memristors, STT-MRAM are actually enabling even more opportunities in this direction. They're also capable of doing exactly what I just described, but they can be more efficient because they can operate on data with minimal movement because they're non-volatile. They don't lose their charge in the cells whenever you read them. As a result, they can be more efficient. And they can also do matrix vector multiplication in their arrays. I'm not going to go into more detail, but I think we should be doing in-memory computation in any memory technology. Let me give you one result. This is end-to-end performance result from a database. We ported a database on our system that is called Ambit, and we see basically more than 4 to 12x performance improvement in database queries in a database that's designed to work nicely on our system. Basically, the algorithm is designed together with the device such that the algorithm is actually executing nicely on the device that I just described to you. Okay, so I think this is very promising. 12x is a performance improvement that's not easy to achieve with simple optimizations. So if you're interested, there's more in the papers that we've written. And this was part of the thesis of my PhD student, Vivek Seshadri, who's right now at Microsoft Research in India. And this is a paper that we wrote recently. Let me give you one more example in a more opportunistic way. So clearly, there are many interesting applications. Genomics is also one, but I'm going to focus on graph processing. Graph processing is really important. There are many applications of it. In fact, graph processing is increasingly used in bioinformatics today. And scalable large-scale graph processing is very challenging because if you actually throw cores at the problem, you don't get a lot of performance. By quadrupling cores, you get very little performance, but you're actually wasting a lot of energy, as you can see. And the fundamental reason is the core of many graph processing algorithms actually have frequent random memory accesses and very little amount of computation. So they really exercise this memory bottleneck that we talked about worse than many other applications, in a sense. So we use the opportunity of 3D stacked logic and memory today. So this is a new technology that's being used. Basically, you have a logic layer underneath memory layers. This is another example of this. Yeah, in the logic layer, you can put compute elements. In the memory layers, you have memory. And the logic layer is connected with high bandwidth, low latency components called through silicon vias today to the memory chips. As a result, you can have high bandwidth, low latency access in the logic layer to the memory layers. And there are other true three-dimensional technologies under development today. This is a fascinating area. Going forward, I think we're going to see a lot more important system changes by more tightly integrating memory and logic into the future. So clearly this exists. Hybrid memory cube, high bandwidth memory are examples of it. I'm going to actually talk about that in a little bit as well. But basically, at the time these memories were becoming new, essentially, we use these memories to actually design a graph processing system. I'm not going to go into the details of this a lot because we don't have a lot of time. You can read the papers if you're interested. And this has actually spurred a lot of future work afterwards on processing in memory. Basically, we took this logic layer and memory 3D stack logic plus memory chips. Internally, it looks like this. This is a logic layer, basically. The chip is divided into vaults. each volt is a memory controller. We basically add a simple processing element in order core to it. You can have accelerators also. And these cores can communicate with each other, and they're programmed using message passing. So what you do is you lay out your graph nodes on top of these memory that's controlled by the cores. And then if you want to update a graph location, you basically send a message from one core to another core such that the core that houses that memory location, that graph location, actually does the update. So basically, we don't move the data. We move the computation to the data. Basically, you move the functions to the data, essentially. Of course, to be able to do this nicely, you need to be able to map your data nicely such that you minimize the movement of functions and also potentially minimize the movement of data, because you have to move some intermediate data to do the operations. And of course, to be able to scale the system, you're bottlenecked by the size of this memory. Today, we're at 32 or 64 gigabytes. So if you really want to have 1 terabyte, you need to connect many of these 3D stacked chips together and then do the layout or graph partitioning on top of it. I'm not going to go through these details. This is actually a very fascinating full system design. This is another example of the algorithm architecture device co-design that I mentioned earlier. And there's a lot in the paper where we talk about this. So we changed the programming model to be message passing, for example. We talk about message passing primitives. We do prefetching inside the device itself so that we can exploit the bandwidth, etc. I'm not going to go through details, but I'm going to show you that this system looks nothing like existing systems, in the sense that in existing systems, you can clearly define the boundary between processors and memory. These are processors, these are memory. Whereas here, processing and memory are tightly coupled. Each device can do processing and memory at the same time, and those devices are interconnected with each other. As a result, very high amounts of memory bandwidth are available to 512 cores in the system we evaluate, 8 terabytes per second. Whereas at the time we evaluated the system, the best system had only 640 gigabytes per second. The reason is we have tight connections between processor and memory, so we can enable much higher bandwidth in the system to the processors. And I'm going to give you the end results, because if I have to talk about this, it will take a lot of time. But the end result looks like this. You get more than 13x performance improvement on important graph processing algorithms, which I believe is a lot. And the reason is you can actually take advantage of the high memory bandwidth over here. And the energy reduction is actually commensurate. You get more than 8x energy reduction in end-to-end algorithms for graph processing. Now, later work, you can see that this work was published in ISCA 2015. In fact, it was done in 2013. Publication happened 2 years later. But basically, later work built on this work, they basically proposed better algorithms for graph partitioning, better algorithms for inter-core communication, better algorithms for load balancing. And if you actually do all of those things that later work did, then you get up to 100x or more. So actually, it's very promising, in my opinion. You get 2 orders of magnitude higher performance. And also, at least, the later work also showed that you get close to 2 orders of magnitude reduced energy consumption in these workloads if you actually build a system that looks like this. Okay, let me quickly talk about one other work that we have done, and hopefully we're going to conclude after that because we don't have a lot of time. But basically, later, this is changing the system a lot. We also wanted to understand, what if we don't change the system a lot? What are the steps we can take to get to 100x? Can we actually go to 2x, 3x first with little changes to the system? And that's the goal of this work over here. So we wanted to focus on consumer devices that are important, clearly. Energy consumption is important. And we wanted to focus on some important workloads where, for example, using video playback and capture engines in this call. Now, Google's engine is no different from the engine that we're using right now to have this call. So we're wasting a lot of energy, actually, today, because there are a lot of inefficiencies in how video playback and capture is done in the systems today. TensorFlow is artificial intelligence machine learning framework that's used in essentially all cell phones today also. And clearly, we're using web browsers right now even. So we wanted to understand the cost of data movement in workloads. And we basically found what I said earlier, more than 60% of the total system energy spent on data movement across the memory hierarchy, because we have to bring the data to the CPU first. And we wanted to understand the potential solution of moving computation close to data to minimize the energy bottlenecks. But of course, this is challenging because you have limited area and energy budget in a mobile system. So the second idea is simplifies the problem. Basically, we observe that a significant fraction of the data movement often comes from simple functions like data copy initialization, like we discussed earlier. And we can design simple lightweight logic to implement these simple functions in memory in a small embedded low power core, or small fixed function accelerators, or small reconfigurable accelerators. In my opinion, it has to be heterogeneous going forward. So we're looking into more heterogeneity. And basically, if you do all of that, you get about 2x performance and energy reduction. So I'm not going to go through this in detail, but there's a lot of interesting analysis that you can see. This is machine learning, for example. Actually, more than half of machine learning inference energy spent on data movement, and more than half comes from simple functions like packing and unpacking and quantization, which I'm not going to talk about. And if you actually offload them to memory, you get significant performance and energy improvements. So if you're interested more, you can take a look at this work over here. So there's a lot more work that I'm not going to talk about. Like we're working on climate modeling, for example, and there's a lot of benefit you get. We're working on genome sequence analysis, approximate string matching, time series analysis. These are actually really, really important kernels that are used in astronomy observations, for example, and more. To be able to do all of these, I believe we need to revisit the entire stack, but we can get there step by step. So if you're interested in improvements in this area, we recently wrote this overview paper that was published in December, and it covers essentially a lot of work on processing in memory, and hopefully you will like it. And there's another work that I would refer you to also. Now, very quickly, this is becoming real. So what we're talking about, we're also working with industry in implementing this. So this is one example from UpMem. This is a startup in France. These folks actually take real DRAM modules, and inside the DRAM chip, with every single bank, they have a processor. And this processor has very high bandwidth, low latency access to the bank, and they have many processors, and we're working with them to evaluate the system. Now, I don't have a slide for this, but just yesterday or the previous day in the International Solid State Circuits Conference, Samsung announced that they have a processing in memory chip as well. They call it function in memory, and that resembles something similar to what I described earlier. They use the 3-stack logic layer to actually execute some functions. And they have some detail in their ISSCC presentation, and I will cover that in my later lectures. But if you're interested, you can look at some detailed lectures on PIM. I recently gave a tutorial on PIM in the International Electron Devices meeting. If you're interested, you can actually have a longer talk about that. Okay, so this is the second challenge that I intended to cover. It's really basically how do we build fundamentally energy efficient or data-centric computing architectures. Now, I'm not going to talk about the other two challenges, even though I have slides for them. We don't have time for them. So let me conclude. If we still have time to conclude, I would like to conclude. Is that okay?
Maybe 5 minutes.
Okay, 5 minutes is perfect. Okay, so I'm not going to talk about them, but I will say that those two other things are related to high performance, so that we can solve the toughest and all problems, and personalization and privacy going into the future. So let me give you some concluding remarks, and then I'm happy to take questions. I think there are some questions online. I have time to answer the questions, so no problem. So a famous architect, not a computer architect, said this, and I really like this quote. This person said, architecture should be based upon principle and not upon precedent. And I think this is actually a good thing we should really think about in life as well. Precedent is what came before. Principle is really what is fundamentally good. And I think this architect built a lot of interesting things because he followed principles as opposed to what came before. And this architect is Frank Lloyd Wright. And he did not build this. This is similar to what came before. It's not bad. It works. It's like a system that we have today, right? It works. But it's not efficient, maybe, right? It's not as good as something like this, right? This is falling water. This is really the masterpiece of this architect. As you can see, it is based on some principle called organic architecture. It's actually very close to Carnegie Mellon University, where I first started my academic career as an assistant professor. And okay, I can talk about the principles of this, but there's no question that this is a fundamentally different and principled design. And it leads to some benefits, but it comes at a cost. So benefits usually come at a cost, and you have to pay the cost to actually experience something completely different and beneficial. And that is supposed that has to happen in computing systems also. Now I use some different things since I came to Zurich. I use these boring train stations. So this is an example of a boring train station, let's say. It works. It's okay. It's functional, but maybe it's not as good as this one. This is Bahnhof Stadelhofen in Zurich, and it was. It's a principled design. You can see some principles over here. It's actually based on zoomorphic architecture. This is another principled design. This is Gare do Oriente in Portugal, Lisbon, and this is the City of Arts and Sciences in Valencia. This is the Oculus in the New York City. Which actually cost billions of dollars to New York residents. So there was actually upheaval in New York to actually build it. But So it costs. This is new technology, a new paradigm. It's different from what came before. It comes at a cost, but once the cost is there, nobody cares about the cost. So we need to transition to new technologies such that we can enable something fundamentally better, like I described earlier. And this was all of these structures that I showed you earlier, except for the first boring train station, was designed by Santiago Calatrava, who's an ETH alumnus and architect. So I will also ask the question, do we have overarching principles for computing today? I don't claim to have all of the principles, but I know that the main principle that we use to design our systems today, which is processing, which is a processor-centric design, is not the design that's used by brains, for example, or by nature. Nature is more distributed, more coupled. It couples more memory and logic together. It has a lot more specialization, which is used partially in systems, but it's not just processor-centric. So I believe we need to find and exploit good principles. We know some of these good principles, like data-centric design, all components intelligent, good cross-layer communication, better than worst-case design, heterogeneity, flexibility, adaptability. But in order to reach bigger principles and enable better systems, we have to have open minds more than anything else. So let me conclude. It's time, I believe, to design principled computing architectures to achieve the highest security, performance, and efficiency. We need to discover design principles for fundamentally secure and reliable computing architectures. We need to design systems to be completely balanced and energy efficient. We need to move to a data-centric or memory-centric paradigm and enable low-latency systems. And we need to enable new platforms for genomics, medicine, health, and artificial intelligence. I believe doing this can lead to orders of magnitude improvements. I've given you some examples of this. I believe there's more. This can enable new application and computing platforms like genome analysis platforms that you can hold in your hand and sequence many genomes within real time. This can enable a better understanding of nature as well, which is, I think, important, and who knows what else. I believe the future is very bright. There's a lot of challenges in underlying technology and overlying problems and requirements and applications, but we need to think across the stack and act across the stack so that we can enable a much better future. And I believe we can get there step by step. Okay, I will mention these two works that talk about PIM review and open problems and this tutorial also. And I'll acknowledge everyone who is funding us because the work is done based on that funding clearly. And clearly, a lot of this work has been done by my students and collaborators, and I will acknowledge them. And I will encourage you to read our newsletter that covers a lot more work than what I just described. So I think that's all I have. We took a little bit longer than expected, but hopefully it was interesting, and I'm happy to take questions at this point.
It was a very nice talk. Thank you so much. And we have a lot of questions.
Oh.
So, okay, one of them. Does intelligently scheduled refresh counter Roadhammer?
Okay, that's a good question. And the short answer is yes, basically. So if you are intelligent about which rows you're refreshing, and if you're careful about figuring that out and scheduling them, yes. And we have shown, for example, in the probabilistic adjacent row activation, it's essentially a form of intelligently scheduled refresh. It does counter Roadhammer, but there are more works that are happening right now that happened afterwards, for example, that try to do it even more intelligently. So basically, the short answer is yes. Of course, how do you intelligently schedule? Because it's still a good research question.
So there's another question. What kind of security solutions designs are being implemented currently for V2X communications?
Okay, so I don't exactly know what is meant by V2X communications, I think.
Vehicle to external, I guess.
Okay, I see. Okay. So basically, I'm not an expert in this topic, clearly. This is a little bit different from what I have studied. I mean, they're certainly looking at attestation solutions, as far as I know, ensuring that the devices are, for example, attested so that you can trust the device you're communicating with. And that's a big issue, actually. If you don't trust the device, then you have a problem, right? I think that's one of the issues. But the security challenges of what you mentioned is much broader than that. You need to be able to trust the device you're communicating with. And then you need to be able to ensure that you cannot, for example, do Roadhammer. I think Roadhammer is actually something that can be done by a component that may be trusted, but then that gets somehow taken over in some manner. So Roadhammer actually can enable problems in that sort of communications also. So I think your question is quite broad. there are a lot of security aspects of it, and it needs to be investigated. But clearly, I'm not investigating all of those aspects, and I don't actually know what's currently being implemented in systems. In my opinion, the systems are not really considering hardware failure as much as they really should consider today. But hardware failures are actually becoming a big vector of attack in all systems, including the systems you mentioned.
Another question: is Roadhammer present in SRAM?
So that's a great question also. And the short answer is yes, it is present in SRAM, but it's not a problem in SRAM because existing SRAM systems that are used in processors, for example, they usually have good protection mechanisms like error correcting codes, etc. So it's very hard to launch this sort of attack in an existing SRAM system. Now, that said, there might be some cases where you could launch it. We didn't try it. But fundamentally, SRAM also has this sort of Roadhammer problem. Now, to be able to induce these errors in SRAM, you may actually need to hammer more than DRAM. The reason is today's SRAM cells, even though they're very small, they are more reliable than DRAM cells, even if you ignore the error correcting codes that are implemented over there, because the charge is more reliable in SRAM cells. So I think basically yes, but it's not as big of a problem in my opinion.
Okay. A Roadhammer program targets specific area, rows of the memory. So with noticing high opening rows rate, can the system's security expect its pattern so that it can shut it down?
Yeah. So now I like this mentality because people are now developing solutions to the problem, and certainly that's one potential solution, and that has been published in literature. Actually, it's been done in both software. People propose that if you somehow profile what's going on in the row activations, and if you see a high activation rate, maybe you slow down the software that's doing that. And people have also proposed hardware solutions, memory controller-based solutions to do that. Of course, there's a cost to it, but yes, that's one solution direction. The key question is how do you make sure it's low cost and really fundamentally secure to be able to do that, because you do not want to miss anything when you're doing that. So software solutions tend to miss because they cannot sample at high enough rates. If they sample at very high enough rates, then they're actually very invasive. But hardware solutions are better in that perspective. But I like the idea. Certainly, if you read the Blockhammer paper that's coming up in HPCA 2021, that talks about solutions in that direction.
Okay. Next question: will in-memory computing become commonplace?
So that's a speculative question, clearly. So in the end, in my opinion, yes. I mean, I'm a believer, and I believe in technology in general. Some technology that makes sense, I think, will become commonplace. Let me give you one example. I think non-volatile memory is one example. So we started working on non-volatile memory in 2007, late 2006, and we published the first paper together with some others at ISCA 2009. Basically, we argued that phase change memory should replace DRAM or augment DRAM. And clearly, this has not happened for 10 years, but it happened recently. Intel, I believe Intel actually provided their phase change memory chips that can be used as a replacement for DRAM today, or augmentation for DRAM, and that's going to become more complex. So it takes time, clearly. Something like this took time, at least 10 years. In-memory computing may take longer or shorter, I don't know. But clearly right now, industry is finally understanding the importance of it. As you can see from the announcement that I mentioned, or the paper that was published by Samsung in ISSCC yesterday, or the previous day, I don't remember exactly. I think these are steps that are being taken to enable in-memory computing to become commonplace. Now, how long will it take? I don't know. Another example is GPUs, for example. GPUs at some point were not commonplace, but they became commonplace very quickly within the course of 10, 15 years, right? And as people realize their importance in large-scale parallel computing. I believe in-memory computing will follow a similar direction. And I'm a believer in the technology. So I believe at some point we will see a lot of in-memory computing devices.
Okay, and does Roadhammer problem occurs to when using adaptive processing, resizing of different processor resources such as issue queue, load store queue, and reorder buffer periodically?
Yeah, so that's a good question also, and I think the short answer is, of course, depends on how adaptive it is, right? If you're very adaptive, such that you're limiting very aggressively how many things you can issue to memory, then you may have a problem. But you can usually craft a very simple Roadhammer workload, like I showed you earlier, right? It's actually 6 instructions. Google reduced it to 5 instructions. With 5 x86 instructions, you can actually induce bit flips, and I think resizing of different processor structures do not happen as aggressively unless you're really limiting the memory access rate for some reason. So basically, the answer depends on how much resizing you're doing in your processor structures. Hopefully that's clear.
If some of the questions, too many questions we have here, why is isolation, is it expensive or does it expand the size of?
Oh, okay.
Hello.
That's
Can you
that's
hear me?
Yeah. Well, there was some problem, but I now see the question online, which helps certainly. So isolation of rows. So that's a good question, basically. So it is not a solution for Roadhammer because it's expensive. It really costs a lot, and it has always capacity overhead. So you can isolate the rows with different materials or clearly distance. But if you do that, you're really adversely affecting the size and capacity of a chip, and you don't want to do that because that finishes the DRAM scaling in a sense. And if you use some other materials, and there are proposals about it, people are actually proposing new materials so that you can isolate the rows better. They're usually very expensive today. As a result, these low-level isolation solutions are not employed by DRAM manufacturers because they essentially stop the DRAM scaling, meaning you don't get capacity benefits. You actually lose cost and capacity.
Okay, can capacitor placement prevent coupling?
Capacitor placement. Okay, I mean potentially, but if DRAM design today is very sensitive, meaning if you look at the way these capacitors are placed today, there's really no space. If you want to improve the capacity, you don't have much choice basically. In fact, the access transistor looks like this, and the capacitor looks like this basically right next to it, and there are other access transistors surrounding it today in DRAM. So you don't have much space to play with. It's a really high form of art, I should say, the design of DRAM. Certainly, if you distance the capacitors and the access transistors, you can reduce things. But then we're back to the previous question that you asked, which is isolation. And I don't think anybody is willing to take the downside on area and cost to do that placement.
If someone is interested in memory computation, what are the resources for learning it?
Okay, that's a good question. I think I already provided you some resources. Basically, I would recommend watching my computer architecture lectures that I mentioned. You can actually find it on my YouTube channel. And there's a lot that's dedicated to memory. In fact, I start the different from a traditional computer architecture course. I start my master's class starting with memory, and I talk about in-memory computation a lot. I'd recommend watching those because they go into a lot more detail than what we talked about. And I would also recommend reading a modern primer in processing in memory, which is a 40-page paper that talks about processing in memory that we recently wrote. It has a lot of references also to work in the field that you can see in that paper. So I would start with those two things, and hopefully they will give you a lot of ideas and a lot of research directions as well, because in my lectures I talk about a lot of open research directions as well. And I would also mention that some students whom I did not know before, who did not take my class, got inspired based on those lectures, and some of them are actually my PhD students right now who are working on the topic, or they're working on the topic remotely in some way.
Okay, which benchmarks are good to stress the current memory architectures?
Oh, okay. Well, I think almost all important and interesting workloads, I will say. So databases, genome analysis workloads that we mentioned, graph processing workloads. Of course, you need to have large data set sizes, right? Clearly, if you run a database with 1 megabyte data set size, you're not going to stress the memory system. You need to run the database and graph processing and genome analysis with a respectable database data set size. It could be, I don't know, 32 gigabytes. It could be more. Even a lot of these workloads have much larger data set sizes, but all of them essentially, like we mentioned, the Chrome browser is another example. Machine learning workloads, a lot of neural networks are actually very data intensive. Again, if you choose a very small network, it's not interesting. If you choose a large network, which is really the state of the art, then it becomes memory intensive. So all the state of the art workloads that are interesting, I believe, maybe all is very strong, but almost all state-of-the-art workloads with large data set sizes are actually stressing the memory architectures. That's why we see results like what Google presented, right? All of the workloads that they showed are memory intensive.
Can in-memory computing will replace the traditional computing?
Okay, that's a good question. And I think the answer here, I will say, is not necessarily. Basically, I think there are certainly workloads that are very compute intensive. And I believe there's a need for heterogeneity, meaning in cases where you are memory bound, you should really do in-memory computation. In cases where you're extremely compute bound, I believe you should really do it on a system that's really designed just for computation extremely efficiently, meaning that we really need to have heterogeneity. So I don't believe that in-memory computing itself is the solution to all of the problems that we have. It's really part of the solution in a much more heterogeneous system.
Is it possible to create Roadhammer attack on an SSD?
So that's also a good question. In fact, one of the papers that I showed you earlier tried to do that. I think it's much harder. So we actually did a lot of work on SSDs, and we showed that Roadhammer type of phenomenon, redisturb phenomenon, exists in SSDs. In fact, we were working on SSDs, flash memory, before we started working on Roadhammer. And we saw a lot of redisturb issues in SSDs. And we said, okay, maybe it happens in DRAM also. And we were lucky to find that it does happen in DRAM. But SSDs, yes, there's a lot of redisturbance. But to exploit that is really hard because an existing SSD controller does a lot of error correction and a lot of voltage optimization, a lot of refreshing to ensure that this sort of issue doesn't happen. And also, even if it happens, exploiting that at the higher levels of the software stack is going to be much harder because SSD is somewhat decoupled. So if you look at DRAM, main memory, whatever bit flip you get immediately affects your data structures or system data, right? Or user data. Whereas if you look at a bit flip in an SSD, a bit flip, yes, your data may get corrupt, but your data structures will not be affected. So your running programs may not have access to it immediately. So I think I have not seen a Roadhammer attack on an SSD because of these reasons at this point. But fundamentally, there's no reason why it's not possible. But practically, it's going to be really hard.
Okay, could you share the slides? One question. Could you share the slides?
Oh, okay, I see. Yes, I'm happy to share the slides. I will post them on my website. If you go to my website, I have a talks page, and I normally post these on my website. But I'm also happy to send it to folks. Of course, there are people who are listening that are not on an email list. So I think probably the best place to find them will be my website and the talks page. But I'm happy to send it also to organizers.
Okay, maybe one last question. How in-memory computing can be used in blockchain technology? This is the final last question. Let's make it the last question.
Well, so this is, I don't know. I mean, certainly blockchain is also memory intensive, right? Whenever you're doing computation. So the short answer is I don't know how exactly, but whenever you're doing operations that are memory bottlenecked, you can push them to the memory side, certainly. But it needs to be investigated. I think applications like this need to be investigated for in-memory computation.
Okay. So I would like to thank you for this nice presentation, the talk, very interesting. I think we have a lot of questions coming, and many students started interested in this topic. Thank you so much. And I think I'll just finish it up here.
Okay.
So
Yeah, thank you. Thank you very much. I appreciate
thank you.
questions also.
Thank you so much.
Yeah, thank you.